Okay, I want to thank you guys for being here. I'm going to talk about the science behind the Observing Olympics telescope program and talk a little bit about some aspects of things that most of us don't really get involved in, namely cosmology. So I'm going to try to make this a succinct talk, which is something I'm not known for. So I might be racing through some of it. If you have some questions, ask me later, or I'll be up at the Observing Olympics table tonight after the meeting if you want to discuss some of these subjects. This is the pen that Eileen Myers has designed. I don't do this program by myself. She is my other half of this program, and for the 2 or 3 people here that don't know Eileen, would you stand up and let them see you and give her a big round of applause, because in every club there's a few people that make that club work, and Eileen is one of them. It's Stellafane. This is the observing program. I've tried to include a little bit of everything, namely quasars, galaxies, globular clusters, et cetera, and I've been told that this is a difficult list this year. So far, we've only handed out 11 or 12 pens, and I'm catching a certain amount of abuse about it's difficult. It's name intimidation. I've got 3 quasars on there. One of them, unfortunately, is too low in the horizon behind the trees. But the other 2 are bright. They're like 14th magnitude, 15th magnitude, which can be seen in small telescopes. And if you see a quasar, you're seeing something fantastic. You're seeing a miraculous thing in front of your eyes, and I'll talk in some detail about that in just a moment. Also, given the fact that people are having so many difficulties with the list, those of you that observed only 10 objects will get a pen. And tonight might be the night, because it looks like it might be some semi-clear skies again tonight. So for me, I've been coming here 9 years, and I've never seen 3 nights of observing at Stellafane. So it's looking good. These are the pens that we've handed out so far. Next year, we're going to do the best of the best, and I'm going to make it exceptionally easy. So everybody should be able to get an observing pen next year. Quasars, first thing I'm going to talk about. And to understand quasars, you have to know or understand something about cosmology. A lot of astronomers kind of shy away from cosmology because a lot of it is theoretical. But there is also a lot of good science behind those theoretical aspects to support what the cosmologists are saying. And quasars are very, very unusual objects because they're very bright and they're very distant. Most of the objects that we look at in the night sky are either thousands or millions or maybe tens of millions of light years away. Quasars are billions of light years away. And that's just a number, but to kind of put that in context, 1 million seconds of time is about 11 days. 1 billion seconds is over 33 years. So if you see a quasar, you're seeing something exceptionally distant. They're not very pleasing. They look stellar. They're not really a pleasing object to look at, but when you realize what you're looking at, that makes them fascinating. So there are several models of the expanding universe, and I don't want to spend a lot of time on this, but the closed universe, where the universe will end up coming back to a big crunch and start over with, most astronomers don't believe that anymore. The flat universe seems to be the present norm right now, which means the universe will expand out to infinity and there is enough mass to eventually stop the expansion of the universe. In 1924, Edwin Hubble discovered that galaxies, which they called white nebula at the time, that galaxies, the Andromeda Galaxy, Barnard's Galaxy, NGC 6822, were external to the Milky Way. They were separate from our galaxy, which had not been thought of before. Before Hubble came up with that, when astronomers looked up at the night sky, they perceived they were seeing the entire universe. In 1924, Hubble stopped that. Then in 1929, he discovered the universe was expanding, and expanding in a linear fashion. And today we call that Hubble's constant or Hubble's law. And it amounts to 70 kilometers per second per megaparsec. And what that really means is that every 3.26 million light years, the universe expands 70 kilometers per second. So the further out you go, the faster the universe is expanding. In the 90s, 1997, 1998, two men independently discovered that at some point the universe is speeding up. So Hubble's constant goes out to a certain distance, and they've recently found out that that increase in expansion in some directions is 4 billion light years out, other areas is 6 billion light years out. But it is speeding up, and they discovered that by finding that type 1a supernova stars are fainter and dimmer than they should be at cosmological distances out towards the edge of the universe. And the key behind that is that type 1a supernova are dwarf stars that are bleeding material off of a companion, and it reaches a certain limit called the Chandrasekhar limit, which is 1.4 solar masses, and the dwarf collapses and explodes. And since a certain definite mass causes the explosion, the luminosity is roughly the same for all type 1a supernova. And if you know what the luminosity is, you can use that as a candle to measure the distance. And these objects beyond a certain distance are too faint, and we call that dark energy. And we don't know what dark energy is. The folks at McDonald Observatory are leading the charge with the Hobby Eberly 10-meter telescope, but it's a relatively new concept, and we don't know why the expansion is taking place, but it definitely is. So right now, dark energy accounts for about 70% of the universe. Dark matter, which is gravitational effects for planets and galaxy clusters, accounts for about 25%. Baryonic matter, which is atoms, neutrons, protons, electrons, the matter that we know about, we can only account for about 5% of the universe, which is a rather strange position to be in. But nevertheless, that's where we are right now. The distance scales, there are several of them. I've narrowed it down to several. The luminosity distance is inaccurate because the light photons are stretched, redshifted, so distant galaxies appear to be too faint. So that throws our distance estimates off. The annular diameter distance, galaxies were much closer when we saw them, but now the galaxy is further away. So they appear to be too bright when in fact they should be fainter. There's a new concept, a relatively new concept, it's called co-moving radial distance or co-moving distances. And it's a concept that a lot of cosmologists use, but proper distance relates to where an object is now in relation to where it was. And that takes into consideration the expansion of the universe. So a couple of objects over here on the right. This shows the Doppler redshift. Objects moving away from us have their spectral lines shifted to the red end of the spectrum. If they're coming towards us, they're blue shifted. And if they're close by, the Gaia spacecraft is using this extensively, is trigonometric parallax, where they take a measurement 6 months on one side of the Earth's orbit, and then 6 months later on the opposite side, and they measure the shift in stars in the background. And if that shift is 1 arc seconds, then that distance is 3.26 light years. That is 1 parsec, 1 parallax second. So that's where parsec comes from trigonometric parallax. So during the universe's 13.8 billion year existence, the universe expands with time. While light from objects approaches the Earth, the universe is expanding away. So we got light coming this way, but the universe is going that way. And a common misconception is that the universe is 13.8 billion years old. That's almost a given. So people think if the universe is 13.8 billion years old, then 13.8 billion years must be the age of the universe, because that's how old it is. That is incorrect, because that light that's coming towards us that takes 13.8 billion years to get here, that universe is expanding while that light is coming this way. And it's expanding faster than in certain areas than the light is coming this way. And that's the fallacy that people have. They see a redshift, a Z, which stands for redshift, and they think, well, that's the age, but that's also the distance, and that is incorrect. And hopefully, I can make that plain. Light at the edge of the universe was emitted 13.8 billion light years ago, when the size of the universe was only 2% of its present size. So you got several things going on. You got a universe this small versus one this big now. You got light coming this way, and you got light going that way. And you've got some heavy hitters down here that attest to this. So again, it's incorrect to confuse light travel time with light travel distance. How do we know the universe is 13.8 billion years old? 2 ways: by combining the cosmic microwave background. And that is a measure in radio waves 380,000 years after the Big Bang. And it is very accurate. It's accurate because at the time the universe was very small and it wasn't expanding that fast, so we can see that light. Today, the edge of the universe, they figure, is expanding 3 times the speed of light. We'll never see that light. But back when the universe was small, we could see this cosmic microwave background. Also, the expansion of the universe using Hubble's law and dark energy. By combining the two and backtracking, we get complementary information, and both aspects come up with 13.8 billion years as the age of the universe. As far as quasars go, how do we know that they're so distant? Well, here's a quasar that's in the Virgo cluster, or behind the Virgo cluster, and its distance is 2.1 billion light years. And here's one that's 22.8 billion light years away. You can see the difference. You would expect more absorption lines of hydrogen with a more distant object, and that is exactly what you see. This slide right here refutes Halton Arp's idea that the redshift had nothing to do with distance. And this very graphically shows that this object is more distant than this object. Brian Cox, who is an astrophysicist from England, came up with a beautiful graph. It shows the edge of the universe from our perspective in all directions is 46.5 billion light years. That means that our universe is about 95 billion light years in diameter, as best we can tell. And currently, as I say, the outer portion of the universe is expanding faster than the speed of light, and we can only see light that has had time to reach us. The outer regions of the universe, if it's expanding 3 times the speed of light, we'll never see that because we can't exceed the speed of light within the universe. What it's expanding into, it can be any acceleration rate. It can be faster than the speed of light, but within the universe, we cannot exceed the speed of light. So, JADES GSZ14Z is the most distant galaxy that we know of as of May of this year. Its light was emitted 13.5 billion years ago, which was only 280 million years after the Big Bang event, when the universe was only 2% of its present size. Its proper distance then was only 2.67 billion light years from where the Earth would have been. The Earth and Sun did not exist then, but it would have only been 2.7 billion light years away. Its light travel time, it took 13.5 billion years to get here, but during that 13.5 billion years, its current distance is 33.9 billion light years away. Its redshift is over 14, which is incredible, and that's a picture of what it looks like. All of the galaxies out there or most of them are what you would expect. They haven't had time to form into nice spiral structures. They're also building stars at a frenetic rate, 40 times what our Milky Way galaxy is doing. Although there are some galaxies out there that are nice spirals, and the astronomers are having a hard time explaining that. They're also finding high oxygen levels out there, also have a difficult time explaining how that could be, that element could be built to such degree in such a short amount of time. And again, this just shows the expansion of the universe. Where it was when this was formed and the light started this way and where we are now. 3C273 is the brightest quasar on the list. Its distance is 2.4 billion light years. It's the one that's too far set in the west for us to view. I didn't take into consideration the pine trees. But it's an easily seen object. And to give you another idea of how bright, how massive and bright these objects are, if 3C273 was the same distance as Pollux, one of the head stars in Gemini, the constellation, which is only 10 light years away, if that quasar was where Pollux is, it would be as bright as the sun. We would never see a night sky. That's how powerful that object is. 3C Markarian 205, which we looked at the other night, and a lot of you are shying away from. It's in a very bright galaxy, namely NGC 4319. That's a bright galaxy. 4291 is even brighter galaxy. But the claim to fame for this was that Hamilton Arp used this as the premise behind his redshift theory, where he stated redshift had nothing to do with distance, that redshift was newly formed matter that was formed in the heart of active galaxies, and those galaxies expelled that material. And you see that light bridge? That was the crux of Arp's theory, that this quasar was shot out of this galaxy, and that light bridge is a result of it. On the opposite side is the anti-ejection for the quasar. And a lot of people, or a certain number of people, believed him. I got to know Hamilton Arp myself. He's a very nice man. He was at the Texas Star Party in 1995 in the 2005 session. And he said that he didn't expect people to believe all of his theories, but he did not expect to live to see any of them proved. Today, hardly anything or hardly anybody believes in his theory. We know now that this light bridge is light from this quasar that's way in the background, shining through the outer arms of the spiral galaxy, which is in the foreground, and it appears to look like a light bridge. But it's not. The two are at vastly different distances. The quasar is actually over 14 times more distant than the foreground galaxy. And you can see it here. This is I elevated this in color so you can see something I had not seen before, but here's the tidal arm coming all the way down here. I don't know if y'all can see that, but that's kind of interesting. 4319 is a disturbed galaxy. They don't know what disturbed it or what caused that. But nevertheless, there's the quasar right there. And it's easily seen. We saw it in Eileen's 13-inch telescope the other night. We were looking through another telescope, so we only had about 6 or 7 inches of aperture. But we were still able to see the quasar. So I would encourage you folks to try and see this. B.L. Lacerda. This is another type of quasar, but it's called a blazar. It's called a blazar because the emission that comes out the polar regions of the black hole, the massive black hole in the center, that emission is pointed right at us. So we're looking down the throat of that strong emission. And it gives off a featureless spectrum, which is different from quasars because their spectrum is full of material, of absorption lines and all kinds of emission lines. B.L. Lacerda is 900 million light years away, and it's when you look in the telescope, it looks like 14th magnitude double star. And then you figure out that the westernmost member of those two stars is the blazar, and away you go. And we looked at it last night, and it wasn't particularly difficult. I put this at the end of the handout. I have this in the Texas, the TSP Advanced Observing Program. And this is a quasar APM 8279 plus 5255 A, B, and C. There's 3 members to it. And it's a gravitational lens, which is how we're able to see it. But its age, its light was emanated only 1.6 billion years after the Big Bang. Its light has been traveling to Earth for a little over 12 billion years. And during that 12 billion years, it expanded with the universe out to a proper distance of 23.5 billion light years. That is halfway to the edge of the universe. Its magnitude is 15.5, and you can see it in amateur telescopes. That's pretty heady stuff. To be able to see with your own 2 eyes an object halfway to the edge of the universe. That turns me on for visual astronomy anyway. And if y'all want to check on some of this, there's a guy that you can get him on the internet, Ned Wright. Has a distance calculator, and he will give you the parameters. You can put in flat, open, closed universe, whatever your Hubble constant is, if it's 70, if it's 68, whatever, and you can come up with these distances for yourself. You can do that with any of these objects, and that's what I've done here. I'm using his information to determine these distances. All right, that's a little bit, or maybe a lot, about quasars. Galaxies, these are the galaxies that I have on the advanced program. And a little bit about how galaxies are called or named. It's called Hubble's tuning fork. Edwin Hubble also came up with a classification scheme for galaxies. And basically, there's 2 different types. There's regular spiral galaxies, then there's barred spiral galaxies. So this is the spiral structures, And then these are the elliptical galaxies, which are spherical and not flat like the spiral galaxies. Hubble thought that the galaxies progressed from elliptical nebula, that these turned into normal spiral galaxies, like these. And he was wrong. We know today that actually spiral galaxies collide and merge and form into elliptical galaxies. But to this day, these are called early type galaxies. These are called late type galaxies, based on Hubble's classification, even though it was wrong. There's one other in here. You've got SO, or lenticular galaxies, which is a combination of ellipticals and spiral galaxies. And these are easily determined if they're edge on, if they're face on. The classification gets a little more difficult. And then a Russian astronomer, Gerard de Vaucouleurs, improved on this with ring structures and spiral structures and different classifications. Some recent discoveries that I found were kind of interesting. 50% of galaxies are found in clusters. Spirals often have an inner rotational region, which is diametrically opposed to the outer regions, which is not what you'd think would occur in a spiral galaxy. They think that what causes that is a past interaction with another galaxy, which mixes up the rotation of the galaxy itself. Elliptical galaxies are found to rotate more slowly than expected, and they think that is due to a phenomenon called anisotropy, which means the cluster is moving at a high rate of speed through space, and as such, it tends to flatten it. And Omega Centaurus is a classic example of that. If you look at Omega, it is very flattened. It's not round, it's flattened, and that's thought because of the fast movement through the interstellar medium. And then dark matter, which I've just touched on but not really talked about because I don't have time. But dark matter, typically, they're finding the virial, or the total mass, is 10 times the luminous mass. And the thinking is that dark matter doesn't affect or doesn't have anything to do with baryonic mass as we know it, but it does affect gravity in some form, fashion, or another. NGC 7793, it's a face-on spiral galaxy. Face-on galaxies are always a little tough, but I put this in there for those of you that hopefully some of you are enjoying it anyway. It's called a flocculent spiral galaxy because its spiral structure is not well formed. You don't see well-formed spiral arms out of it. It has a nuclear galaxy or nuclear star cluster in the center, and there's a lot of activity going on here. It has a luminous X-ray pulsar. It has a microquasar, which is inflating a bubble 980 light years in diameter. That microquasar, 980 light years in diameter. Our nearest star is 4 light years in diameter. So that is a very energetic event in a very poorly formed galaxy. And it's kind of got astronomers wondering, how did that happen in a galaxy that really is so ill-formed? There's star formation all over the place. You see the H2 regions are everywhere. Not just in the spiral arms, but all over the place. So this is a messed up galaxy, and I put it in the program because it's also, being a messed up galaxy, it's an interesting galaxy. The Draco Trio is one that a lot of people have enjoyed looking at. A lot of people don't know the Draco Trio is there. It's debatable whether these galaxies are gravitationally attracted to each other because the light year distance span between them is about 28,000 or 28 million light years. So it's debatable whether they're actually gravitationally bound or they're just happen to be traveling through space together and give the appearance of being attached. Emission reflection nebula, these are the ones that we included in the observing program and should be fairly easy. The North American Nebula is a naked eye object. I mean, if you just look up at the northern part of Cygnus near Deneb, you can see it without even a filter. And then the Veil Nebula is easy. I've got the western loop and the eastern loop of the Veil Nebula. And the Veil is the product of a supernova that went off about 10,000 light years, or 10,000 to 20,000 years ago. The progenitor, the star that went supernova, they figure it was 20 to 30 solar masses in size. They've never found any relic of that star, and the thinking is that it no longer exists. There is nothing there. They have hunted and hunted and hunted and have been unable to find anything as a result of the supernova explosion. It is expanding about 932,000 miles per hour, and the Hubble Space Telescope has actually measured that expansion in micro arc seconds, which is kind of interesting. But what is really interesting is that the thinking now is that there's two supernovae that went off within the same area, because you've got a shell here, and you got a shell here, and you got something down here. And within this area here versus the external portions, you have a higher magnetic field. You have a stronger X-ray infrared emission. You have elevated hydrogen alpha, elevated oxygen 3 emission within portions of the Veil Nebula. So the thinking now is that we're not looking at one supernova explosion, but possibly two supernova explosions. And particularly this little loop down here is very interesting to look at. The North American Nebula, as I say, is a naked eye object. Its distance is 2,590 light years, and the Gaia spacecraft has measured that with a high degree of accuracy, so we know that is correct. I say here, use a nebula filter, no telescope. You can use your naked eye and see it actually without a telescope. This star right here is an illuminating star, and the name of that star is Bayaman star, which when the Spaniards discovered the Bahamas, they called the Bahamas Bayamas. So since this star is where the Bahamas should be in relation to the United States, they're calling that Bahamas star, which is kind of interesting. It is a binary star. Both of them are massive type O stars with a V magnitude of 13, so they're easily seen if you want to use a telescope. And that is the primary illuminating star for all of this area here. The other night we did look at it in Irene's 13-inch telescope, and you can see the Cygnus wall here. This is the most dense portion of it. You can see that fairly well, and you can see this portion which equates to Mexico. But spend some time with it, and if you get a good sky, good optics, you can see the pelican and the pelican's beak. So that's, and it's huge. It's something like 10 times the size of the moon. So this is an area that you can wander. If you use a telescope or binoculars, you can wander around inside of it and pick up detail. Barnard's Galaxy, NGC 6822, is a member of the local group. It is nearby. Its distance is only 1.5 million light years away. Diameter is only 7,000 light years away. It is dark matter dominated, which I referred to earlier. Its mass to light ratio is 30 to 40 times. So the mass is 30 to 40 times the light that we can see. So by definition, that means it is dark matter dominated, which most of these dwarf galaxies like this are. There's only one supernova remnant, and it's in here. I've never seen it, and I don't think anyone has visually. That's what it looks like expanded. Most people think that Hubble 3 is a supernova remnant, but that's a massive star cluster that's pushed out a donut-type emission structure, but it is not the results of a supernova, which is what most people think. The galaxy is also called a backsplash galaxy because it is in orbit, or they think it's in orbit around the Milky Way galaxy. It passed inside the Milky Way's virial radius about 4 billion years ago. A virial radius is any time you get an enhancement of over 200 times stellar background versus the interstellar background, then that's considered part of that galaxy. So it's presently falling inward and getting closer to the Milky Way. A few dark nebula. These are binocular objects. This is Barnard's E, which Al showed us the other night in his binoculars. It just looked like dark ribbons, up near Altair in the constellation of Aquila. Don't use a telescope because it's too big and it's too faint, but use binoculars and you should be able to see it. Same thing with the S Nebula and Barnard 68. Both of these are in the same field. And if you want to see a dark nebula naked eye, well, there it is, the Snake Nebula right here, or the Pipe Nebula, and then the Snake is right here, and Barnard 68 is right there. So if you do use a telescope, you can see both of these in the same field. And as I say, this is a prominent naked eye object. It looks like a pipe. Here's the handle of the pipe, and there's the bowl of the pipe. Again, naked eye, dark nebula. Dark nebula are difficult because they're absence of light, basically. William Herschel thought they were void spaces. He thought they were holes in the universe. Edward Barnard, E.E. Barnard, took that study further and determined that they were clouds, that they were blocking out stellar material in the background, but there were foreground clouds that were obscuring the background. But he didn't know what that obscuration was. In 1936, Trumpler determined that it was dust, that these are dust clouds, and that dust is obliterating the stellar background. But you need a strong stellar background in order to see this. If you don't have a bunch of stars, then you're looking for black on black and you'll never see it. But maybe you can see it if you photograph it. Planetary nebula. I understand some of you folks have been having a lot of fun with the planetaries on this list. But particularly this one, the Red Spider Nebula, that is one of the most energetic planetaries that we know of. The Pembert Planetary Nebula Classification Scheme is based basically on the chemical, spatial, and kinematic properties based on the mass of the progenitor, the star that went planetary nebula. And planetaries are stars with masses anywhere from 1 solar mass, like our sun, up to about 8 solar masses. Anything larger than 8 solar masses, you're not going to get a gentle efflux of material. You're going to get an explosion. Where the core, the hydrogen converts to helium, the helium to carbon, nitrogen. Eventually you get radioactive nickel, which goes into cobalt, and that goes into iron. Iron explodes. That's above 8 solar masses. But planetary nebula are a more gentle ejection of material, and Pembert classified these in 5 different classifications, and I won't read all of them. But basically, type 2 is the most prominent. It has an intermediate disk population, and most of the planetary nebula are in that group. Type 4 is objects in the halo above or below the plane of the galaxy, and type 5 are planetaries that are located towards the galactic center of our Milky Way. But this is a scheme that they came up with in 1978, and it seems to be the prevalent classification schemes for planetary nebula to this day. And you see 6537, the Red Spider Nebula, the one in Sagittarius that I think people have been having a hard time seeing. But it is a type 1. It's helium and nitrogen overabundant. That tells us right off that the progenitor star was a very massive star. In this case, they think it was about 6 solar masses when it went through the planetary nebula stage. Its temperature is very interesting because the temperature of our sun, depending on whether you use the Celsius or the Fahrenheit scale, is about 10,000 degrees. The surface of the illuminating white dwarf in the center of this nebula has been rated up to 250,000 degrees of temperature, and some scales have it up to 500,000 degrees. That is extremely, extremely energetic for a planetary nebula, which is ionizing all of this emission structure that you see. Its luminosity is 10,000 times that of our sun. And its only age about 1,600 years in the making. And typically, most planetary nebula cease to exist. Their expansion gets so far that they just simply disappear in about 50,000 years or so, about what it takes. And then globular clusters. These are very massive groups, collections of stars, anywhere from, say, 100,000 to several million stars in a very compact cluster group. And the thinking how globular clusters formed, if you take our solar system, our sun formed out of a nebulous cloud, and the parts of the nebulous cloud that didn't collapse into the sun formed the planets. Same thing with galaxies, with spiral-type galaxies. The material that did not form into the spiral galaxy formed globular clusters. And that's the thinking of where they came from, and they orbit in and around and through our Milky Way galaxy. And today, now, there's approximately 170 globular clusters in our Milky Way galaxy. Some spiral galaxies, like M87, huge spiral, huge disk, spherical galaxies, have upwards of 13,000 globular clusters. These are composed of old red stars, and a fairly recent finding is they're finding that many of them have multiple stellar generations. It's been thought for years that there's only one generation of stars, and they're all old. They're older than 10, 11, 12 billion years old. We're now finding that some globular clusters do have a second generation of stars that formed from the first generation, which is a relatively new discovery. They're able to stay together because there's so many stars that imparts a strong gravity, and that strong gravity keeps the globular cluster together. The classification scheme, it's kind of like the galaxy classification scheme. This is based on photographs, it's based on visual appearance, and it's not always as accurate or not always what you would think. But class 1 are the most densely formed clusters, and then class 2 is less dense, so on and so forth, until we come down to Palomar 12, which is a class 12, and you can see dark space between them. But you can see this one looks almost as dense as, say, some of these up here. So that's where the classification scheme with not only globular clusters, but with galaxies goes awry because they're either visual or they're photographic, and whoever's taking the photograph has a different idea, maybe from somebody else. But nevertheless, this is if you see a globular cluster and it's classification 8, then that's in general, more densely packed than a classification 4 cluster. NGC 6144, I put this in because this is a globular cluster right next to the very bright, massive Messier 4 in Scorpius. And this is one that most people don't know about. M4 is here, 6144 is right there. It's right very, very close to the bright red star Antares. It's faint because it's located behind the Rho Ophiuchus dust cloud, or Sharpless 2-9. And its age is typical for globular clusters. It's over 12 billion years of age. It has 2 X-ray sources, and interestingly enough, it has 3 post-AGB stars. AGB stars are stars that are getting ready to go into a planetary nebula stage. Globular clusters shouldn't have planetary nebula because all of the stars, or the stars in planetary nebula, are very old, small stars. The stars that would have formed planetaries have been gone for billions of years earlier, so there really should not be any planetary nebula in globular clusters. Nevertheless, our Milky Way has 4 globulars that do have planetary nebula in them. M22 is probably the most popular one that people are aware of. But it's interesting because this is a poorly formed cluster, and it has 3 stars that are becoming planetary nebula within this one cluster. So that's kind of a puzzle for astronomers to figure out how and why that happens, and maybe there's more planetaries than in globular clusters than we're aware of. We just haven't found them. NGC 6822 again with star clusters. The main one is Hubble 7 right here. That's a globular, and it's easily seen. If you find these 3 stars here, and they're fairly bright, and then you just use that as a pointer and go up, and if you see something there, boom, you got a globular cluster in another galaxy. And it's really not difficult. As far as the nebula, Hubble 5, Hubble 10, those are very bright. I looked at them in Amelia Goldberg back in Houston, who I do a lot of observing with. She's got a 15-inch telescope, and we can see these 2 nebula without a nebula filter. You can put a nebula filter on them. It helps a little bit, not a lot, but it helps a little bit. But I would encourage you guys to find Barnard's Galaxy tonight, if available, and look for this one, and this one. And I think you'll be surprised. If you look for it and you take the time, you should be able to see it. This dwarf galaxy is very unusual because it has 8 globular clusters in it. It has 157 H2 regions, star-forming regions in this dwarf galaxy. 26 planetary nebula throughout the galaxy and on out. I've got the next slide. This shows some of the advanced program that I have people do at the Texas Star Party. Here is Hubble 7. That's the one that I'm telling you guys you should be able to see. Here's some that I had on the advanced program at TSP, SC 3, 6, and 7. And these are further out, but you star hop. You go out to it, you follow this trail here to there, you go up to these 2, over, and bam, and this can be done. And it takes a little time, it takes a little effort, but as a visual astronomer, if you're seeing star clusters and nebula in other galaxies, it's got to be exciting. I mean, it's got to be exciting. And then lastly, I've got open clusters, and I just centered on Messier 11. This is not really a difficult object, but it's too beautiful not to include in a discussion. It's called the wild duck cluster because it's triangular shaped, and it looks like a flock of ducks in flight at nighttime. And it's a close-up view of it. Its distance is a little over 6,100 light years, has 2,900 members. The brightest star in it is 8th magnitude, and it just stands out. I mean, it just leaps out at you in the cluster. And it has an excess of alpha-enhanced stars, which tells us that these are massive stars that are forming carbon, oxygen, nitrogen, neon, magnesium, your heavier elements, and that is only formed in the presence of heavier stars, more massive stars. So with that, I have a book that was mentioned. It's book volume 1, 2, and 3, the series published by the American Astronomical Society in Sky and Telescope. And this is how people can order it if they want it. It's based on the Texas Star Party Advanced Observing Program. And what I've tried to do there is get people, throw your computers away, star hop, look up in the sky, find the constellation, find the bright star, and then from there, work your way over to where the object is. That way you know where in the sky you are. If you use a computer, you just know it's up there somewhere, but you don't know where. If you star hop, you can find it. If you do it a couple of times, 3 times, maybe you can throw that star chart away and you can do it from memory, which is always the best way to look at things. And then secondly, I try to explain what people are looking at. Because if you look at some dim, faint, and fuzzy, and that's all you know about, well, it's not very interesting. But if you know that it has had 6 supernovae go off in the last 20 years, it's 75 million light years away, it has an active galactic nucleus, and is throwing material out of it, that makes that dim, fuzzy thing an interesting object. So I try to let people know and understand what they're looking at, and that's what we do with the advanced program at Texas, and that's what I've tried to do in these 3 books as well. So a few things to think about, which I just kind of ran across. Astronomy is a humbling and a character-building experience. Carl Sagan, very true. Astronomy is much more fun when you are not an astronomer. Sir Brian May, who's a famous astrophysicist, also the lead guitar player for the rock group Queen. Very interesting individual. He worked on the Pluto mission, asteroid OSIRIS-X mission. He does a lot of astronomy in addition to playing his guitar. The universe is under no obligation to make sense to you. Neil deGrasse Tyson. And then lastly, which I presented here, a cure for many of the world's problems is simply 1 gentle dose of starlight to be taken each night just before retiring, by the famous Leslie Peltier. And with that, I've got a picture of the night sky at the Texas Star Party. This is typically what we see. These light domes that you see down there are 95 miles away in Mexico. We have dark, dark skies down there, and I would encourage you folks to come down and visit with us. I guarantee you will love it. So with that, I hope I've encouraged you guys to try and find some of these things tonight, if available. And with that, I thank you very much for your attention. Do we have time for questions? Any questions? Okay. Sir?
There's an object called Stellafane on one of your slides.
Oh, I just had that's the North America nebula. It's just look there rather than somewhere else. It's the brightest part of that object. Yeah, that's all that was. Yeah. Yes?
What telescopes do you prefer to use, like when you're viewing?
When I'm viewing, the biggest telescope I can get my hands on, but that's not necessarily necessary. What I try to do is present objects that can be seen in 15 and 16-inch telescopes, but they have weird names like Minkowski 147. And so somebody with a 15-inch telescope, I can't see that. Well, yeah, you can if you go out and look at it, or look for it. So aperture is not always the best thing. If you're looking at North American nebula, my telescope's a 30-inch telescope. I can see about that much of this big a nebula. So a small telescope works better with that. So it just depends on what you have and how you like to observe. Yes, sir?
Speaking of a North American nebula, when's the last time, or how old were you the last time you saw it by eye?
Last night. Yeah, last night. You look at Deneb in the northern part of Cygnus, and you look just below Deneb, and it's kind of hazy. You look above Deneb, it's dark. That haze below Deneb is the North American Nebula. Yes, sir, Mario.
One thing you can do, and I've done this and showed it to people who visit, is take an O3 filter, just look with your eye, you
Right.
suddenly see where it is, remove the filter, and then you see it.
Yeah, exactly. And that's what, on the slide, I tell people, use a filter, not a telescope, just use a filter, because it's 10 times the size of the moon. And just use a filter and you can see it and look away. But, I mean, last night, I could see it easily. You know, there's something below it, there's nothing above it. That something below it is the North American Nebula. Yeah. Yeah. The next Texas Star Party is going to be, I believe, the end of May, the last week of May. Is that right, Susie?
No, it's the middle of May.
Middle of May.
The 10th.
May 10th. May 10th. Okay, somebody over here. Yes, Steve.
To your point, Larry, about seeing these things with modest-sized telescope, you don't need a 30-inch.
No, you don't.
At our club, we have a guy who's got a 16-inch.
You always need a 2-inch, I'm sorry.
Oh, well, you
Yeah.
be quiet, mister. I don't got my 8-inch.
Well, we have a guy in Houston. Now, I do advanced observing programs. I try to get people to push the envelope, like look for 15.5 magnitude quasars halfway to the edge of the universe. He has an 8-inch telescope, and I have given him a pen for 24 years. He has successfully observed every list I have given out, and on some of them, he has observed everything on the list. They have to observe 20 objects in order to get a pen. I start out with 40, and as on several lists, he's done all 40 objects, and he's done it with an 8-inch Celestron Schmidt-Cassegrain telescope. So you don't need big aperture to do this. You need patience, black cloth over your head, sit there, study, and we feel like in Texas, if you see it 3 times, you think you see it 3 times, log it and go on to the next one, because you probably did. Yeah.
It can be done here, because I've used an 8-inch here
Yeah.
and found all the objects.
Right, right. Yes, sir.
Speaking of small apertures, I've seen 3C273 with a 4-inch teleview refractor.
4-inch teleview refractor, 3C273. It's the brightest quasar in the sky. It's like 12th magnitude. It's unfortunate it's behind the pine trees. When I didn't take into consideration how late it gets up here. I thought it was going to be up, you know. But yeah, 3C273 quasar, 2.5 billion light years away with a 4-inch telescope. So you don't need big aperture. You know, whatever you've got, just take it out and make it work. Spend the time with it, and you'll be amazed at what you can see. Yes.
How dark does the sky get out in Texas?
Well, I got a little meter. We get down to 22, 23. My first experience at the Texas Star Party, I thought I knew the night sky. I could not find the constellation Virgo. Virgo doesn't have any really bright stars in it, but there are so many stars up there, it all blends in. You know, so it's dark. It's very dark. That's why McDonnell Observatory is there. You know, it's dark and it's dry. We get a typical humidity night is like 12-15%. So you're not looking through an ocean of water. You know, you're looking through just pure sky. Elevation is about 6,500 feet. So it's very nice out there. Yes, Mario.
Just curious, how much is the light pollution from the gas wells burning and the lights they use?
Not so much from the gas wells because they're down low. The problem that we're getting, and it's becoming somewhat of a problem, over in Mexico, there is a factory that has 3 smokestacks that are pulling out white smoke 24 hours a day. And that is affecting things. 10, 15 years ago, I sat down with observing buddy of mine named Barbara Wilson. When the Milky Way was on the horizon, we got a white piece of paper, held our finger up, and just from the Milky Way, we could see a shadow on that paper. The Milky Way was iridescent. About once every 2 years now, we see an iridescent Milky Way. And it's because of that. It's because of those smokestacks. But nevertheless, it's still one of the darkest skies in the country. I would encourage you guys to, come down. We try to get good speakers. This last year we had Stephen O'Meara, David Levy, myself talking one night. Next year we've got Dave Eicher, Diane, can't pronounce her last name, Haneke, yeah, of Sky and Telescope. So it's a fun week. If it's cloudy, you can still have a good time because you got 200, 300, 400 people like-minded like yourself that love astronomy, love the night sky. Everybody's passing ideas off on each other. And no matter how much you think about astronomy or the night sky, I guarantee you're going to learn something at that star party. Pretty much like you do at this star party, or any star party. Okay, thank you again. Yeah.